Everyone, today I'm going to read the chapter Acids and Bases of Inorganic Chemistry, 4th semester. 7.1 Arrhenius Concepts of Acid and Bases. Arrhenius, a Swedish chemist, was the first to define acids and bases in aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, gives hydrogen ions. Accordingly, all mineral acids like HCl, HNO3, and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions. As HCl is dissolved in water gives H positive plus Cl negative. Arrhenius named these acids which dissociate completely in water as strong acids. These are other acids like acetic acid, carbonic acid, and phosphoric acid, which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecules as given below. CH3COOH, when is dissolved in water, is in equilibrium in H positive and CH3COH negative. Same goes with carbonic acid and phosphoric acid. Arrhenius named these acids as weak acid. According to Arrhenius, a base is a substance which contains hydroxyl group and which is dissolved in water gives hydroxyl ions. Thus, substances like NaOH and KOH when dissolved in water dissociate completely to give hydroxyl ions as NaOH in water is equal to gives Na positive plus OH negative. Arrhenius named these bases as which dissociate completely in water as strong bases. There are substances which do not completely dissociate into hydroxide ions. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOH twice, AlOH thrice do not dissociate completely to give OH negative ions. These can be written as NH4OH in water is equal to in equilibrium with NH4 positive ions plus OH negative ions. Hydrogen ions obtained from the acids and hydroxyl ions obtained from the bases combine together to form unionized water. Arrhenius described this combination of H positive and OH negative ions as neutralization reaction. Arrhenius concept is very simple to apply and explains a number of phenomena like neutralization, hydrolysis of salts, strengths of acids and bases. However, there are certain limitations which are described below. First, Arrhenius concept of acids and bases is applicable only in aqueous solutions. This concept fails to explain the acid or the basic behavior of substances in non-aqueous mediums such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Second, Arrhenius concepts fail to explain the acidic character of substances like CO2, SO2 and SO3 etc. and basic character of substances like NH3, Na2CO3, CO etc. Third, Arrhenius concept also fails to explain the reaction between an acid and a base in the absence of water. For example, NH3 gas plus HCl gas is equal to NH4Cl solid. Although Arrhenius concept of acid and bases suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. 7.2 Bronsted-Lowry concept. Arrhenius concept of acid and bases was further improved by Bronsted and Lowry, both a Danish chemist and Lowry an English chemist. In 1923, incidentally introduced the same definition for acids and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as acid is in equilibrium with H positive ion plus base, that is proton donor. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as NH3 plus HCl is in equilibrium with NH4 positive ion plus Cl negative ion. The curved arrows show how electrons must rearrange to result in the transfer of hydrogen atoms from the acid to a base. The unshared pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structure of the reactants and products show that the hydrogen atom which was bonded to chlorine in the reactants is bonded to nitrogen in the products. Thus, a proton has been transferred from chlorine to nitrogen. To act as a Bronsted-Lowry base, a species must have at least one unshared pair of valence electrons so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached through an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. Some other examples of acid-base reactions according to Lowry-Bronsted concepts are HCl plus H2O is in equilibrium with H3O positive plus Cl negative. H2SO4 plus H2O is in equilibrium with H3O positive ion plus HSO4 negative ion. It is important to note that the above examples that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, the water acts as an acid with respect to ammonia. Such a substance which act both as an acid and as well as base is called amphoteric or amphiprotic substance. Similarly, bicarbonate ion behaves as an acid and a base. HCO3 negative plus NH3 is in equilibrium with NH4 positive ion plus CO3 2 negative ion. HCl plus HCO3 negative is in equilibrium with H2CO3 plus Cl negative ion. Other examples of amphoteric substances is hydrogen sulfate ion, that is HSO4 negative. Conjugate base acid base pairs. Let us reinvestigate a reaction between an acid and a base. HCl plus NH3 is in equilibrium with NH4 positive plus Cl negative ion. HCl being an acid donates a proton and forms Cl negative ion, whereas ammonia being a base accepts a proton and forms ammonia ion. Now, the chloride ion has a tendency to accept the protons, whereas the ammonium ion has a tendency to donate protons. In other words, an acid donates a proton and becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as a conjugate base of the acid. Similarly, the acid formed from a base is known as conjugate acid of the base. In the above examples, HCl and NH3, Cl negative is the conjugate base of HCl and NH4 positive is the conjugate acid of base NH3. Acid and bases that are related by the loss or gain of H positive ion are known as conjugate acid base pairs. The Cl negative and HCl, NH4 positive and NH3 are conjugate acid base pairs. We can represent the acid base pairs as acid is in equilibrium with conjugate base plus H positive ion. Base plus H positive ion is in equilibrium with conjugate acid. It clearly indicates that any acid-base reaction would involve the two acids and two bases. These acids and bases are called conjugate pairs. For example, acid 1 plus base 2 is in equilibrium with acid 2 plus base 1. For example, HCl plus H2O is in equilibrium with H3O positive plus Cl negative. In the above example, HCl is an acid since it donates a proton and Cl negative is its conjugate base. Water accepts the proton and hence it is a base. Thus, H3O positive ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. Some other examples of the conjugate acid base are cited below. HNO3 plus H2O is in equilibrium with CH3 positive, H3O positive plus NO3 negative. H2O plus H2O is in equilibrium with H3O positive plus OH negative. H2O plus CO3 negative is in equilibrium with HCOO3 negative plus OH negative. It is further important to note the Bronsted-Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to the ions as well. A careful inspection of the above discussion reveals that first, a substance is capable of showing acidic character only in the other substance is capable of accepting the proton, that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive ion from HCl. Second, not only neutral molecules but cation and anions may act as acids and bases. Third, both Arrhenius and Bronsted-Lowry concept requires an acid to be a source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. Fourth, according to Arrhenius, a base is a substance which gives OH negative ions in solution. NaOH in water gives Na positive ion plus OH negative ion. Whereas, according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, CO3 2 negative ion plus H positive ion gives H3 or HCO3 negative ion. Carbonate ion CO3 2 negative cannot give OH negative ions in aqueous solution. It therefore cannot be Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcomings of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like CO2, SO2 and SO3 with the basic oxides like CaO, BaO and MgO, which takes place even in the absence of water. For example, CaO plus SO3 gives CaSO4. Clearly, in this reaction between CaO and SO3, there is no proton transfer involved in the reaction. Second, the acidic nature of compounds like BF3, FeCl3 and AlCl3. 7.3. Lewis concept of acids and bases. G. N. Lewis in 1923 proposed a more general definition of acids and bases, which is based upon the donation and acceptance of electron pairs. According to Lewis' concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbitals to accommodate one or more pair of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that a substance with unshared pairs of electrons can behave as a Lewis base. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donors and the electron pair acceptor. For example, the reaction between boron trifluoride and ammonia is a typical Lewis acid-base reaction. Now let us discuss in detail Lewis acid. According to this concept, Lewis acid are classified as first, molecules having central atom with incomplete octet of electrons. Boron trichloride, boron trifluoride, aluminium trichloride, etc. are acid of this type. It is clear that the central boron and aluminium atoms have only 6 electrons. Second, simple cations. All the cations are short of electrons and can behave as Lewis acid. Large size cations like Na positive, K positive, Ca2 positive and Ba2 positive, etc. behaves as weak Lewis acid. This is because these have little tendency to accept electrons. On the other hand, small sized cations such as H positive, Ag positive, Li positive ions have a strong tendency to accept the pair of electrons and are strong Lewis acids. In addition, highly charged cations have a higher tendency to accept electron pairs related to lower charged cations of the given metal. For example, Sn4 positive is a stronger Lewis acid than Sn2 positive. Some of the typical examples of Lewis acid-base reactions are given below. Ag positive plus 2NH3 gives AgNH3 twice positive. Third, molecules in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5 and SO3 are Lewis acid where the central metal atom can expand its valence shell. AlCl3 plus Cl negative is equal to AlCl4 negative. SiF4 plus 2F negative is equal to SiF62 negative. SnCl4 positive plus 2Cl negative is equal to SnCl62 negative. SbF5 plus F negative is equal to SbF6 negative. 4. These molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of a double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has the tendency to attract the shared pair of electrons more toward it in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attaches with the oxygen of the hydroxide ion. Similarly, sulfur trioxide acts as a Lewis acid towards water. Lewis bases. According to this concept, Lewis bases may be classified as one of the following type of substance. First, negatively charged anionic species. All the negatively charged species are Lewis bases because they are rich of electrons and have a strong tendency to donate electron pairs. Common examples are Cl negative, O2 negative, OH negative, NH2 negative, etc. The greater the charge density on the anion, the stronger is the base. Second, neutral molecules with one or more than one unshared pair of electrons. Molecules with unshared pair of electrons acts as Lewis bases. For example, NH3, H2O, R2O and R2C double bond O act as electron donor. Third, alkene and alkynes with multiple bonds also form coordinate bonds with metal ions in organometallic compounds. Acid-base reactions according to Lewis concept. Some of the typical acid-base reactions involving the formation of a coordinate bond between a Lewis acid and a Lewis base are summarized below. First, combination between H positive and NH3. Second, combination between BF3 and F3 ion. 3. Combination of calcium oxide and sulfur trioxide. It is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from a double bond on the oxygen atom. Fourth, combination of cupric ion with ammonia. Fifth, combination of stannic chloride with ethers to give an adduct. Lewis acid-base concept discussed above is widely used because of its simplicity in understanding many acid-base reactions. In spite of its wider applications than Arrhenius and Bronsted-Lowry concept, it has several disadvantages which are given below. First, Lewis concept is too general and consider all reactions forming a coordinate bond to be acid-base reactions. This is, however, not true always. According to Lewis concept, some of the transition metals that form compounds with carbon monoxide such as NiCO4, FeCO5, etc. are acid-base reactions, which is not correct. Second, formation of a coordinate bond between an acid and a base is the basis of a Lewis concept. However, the well-known acid like HCl, HNO3 and H2SO4 do not form any coordinate bond with the bases such as NaOH or KOH. Accordingly, HCl, HNO3 and H2SO4 should not be regarded as acid according to Lewis concept. Third, Lewis concept does not give any uniform scale of acid and basic strength. 7.4 Lux flood concept of acid and base. A new concept of acid and base was proposed by Lux in 1939. This concept was further extended by Flood in 1947. According to Lux flood concept, an acid is any substance which accepts an oxide ion, where a base is any substance which gives up oxide ion. Thus, Lux flood bases can be represented as CaO is in equilibrium with Ca2 positive plus O2 negative. PbO is in equilibrium with Pb2 positive ion plus O2 negative ion. Na2O is in equilibrium with 2Na positive plus O2 ion. And Lux flood acids can be tentatively represented as acid is in equilibrium with base plus O2 negative ion. Thus, Lux flood acid-base reactions can be represented as SiO2 plus CaO is equal to CaSiO3. CO2 plus BaO is equal to BaCO3. SO3 plus PbO is equal to PbSO4. P2O5 plus 3Na2O is equal to Na3PO4.